And let's look at a few more examples. Here's a definite integral from 2 to 3 of x cubed plus 2x over 5x squared with respect to x. Now, the difference with this is only subtle from what you've done before. Anytime you have a single term in the denominator, the best way to handle an antiderivative is to break it up into individual fractions and pull constants out. So this is 1/5 the integral from 2 to 3. X cubed over x squared is x, and then 2x over x squared is 2 over x. The only thing we couldn't do before was this part, because we didn't know how to do the antiderivative of 1 over x. So then what do we have? This is 1/5, using the powers rule, x squared over 2, plus 2. Now we know this is the natural log of the absolute value of x, evaluated from x equals 2 to x equals 3. So this is 1/5 of 9/2 plus 2 natural log 3 minus 1/5 of 4/2 plus 2 natural log of 2. Evaluating at 3 and evaluating at 2. When we simplify this down, what do we get? We get 9/10 plus 2/5 natural log of 3 minus 2/5 minus 2/5 natural log of 2. And 9/10 minus 4/10 is 5/10, so this is a half plus, and if we wanted to, we could combine all of these logarithms. This is natural log of 3 to the 2/5, that's natural log of 2 to the 2/5. The difference is the quotient, so we could call this natural log of 3/2 to the 2/5, I guess, if you wanted to, or whatever. Or you can leave them separate. Next one, find the derivative of x to the third over e to the 2x. Well, what we've got going on here is a quotient rule. If you'd rather not use the quotient rule, you can use the product rule. Personally, I'd write this as the derivative of x to the third times e to the negative 2x. Dividing by e to the 2x is the same as multiplying by e to the negative 2x. Now we use the product rule, which is a little easier than the quotient rule. That's 3x squared e to the negative 2x plus x cubed. Now the derivative of e to the negative 2x is e to the negative 2x, and then the chain rule says times the derivative of negative 2x, which is negative 2. So we have e to the 2x, negative 2x can come out of both if we want to, or we can write this 3x squared minus 2x cubed over e to the 2x. Now we want the integral from 0 to 2 of x to the 4th times e to the 2x to the 5th. This is a classic u substitution. We have to let u be the exponent and hope the derivative is taken care of here. So we'll let u equal 2x to the 5th. Then du dx is, bring the exponent down, 10x to the 4th, or du over 10 is x to the 4th dx. When x equals 0, u equals 2 times 0 to the 5th is 0. X equals 2, u equals 2 times 2 to the 5th, so 32 times 2 is 64. So this becomes the integral from 0 to 64. X to the 4th dx is du over 10, so that's 1/10 e to the u du. And that's 1/10. The antiderivative of e to the u is e to the u, so it's e to the u evaluated from 0 to 64. So that's e to the 64, which is a huge number, over 10, minus e to the 0, which is 1. Or e to the 64 minus 1 over 10. Okay, one last example. This is exactly the same as the one in the homework because it's such a nice problem. We're looking for the area under the curve, and the curve looks like this, x e to the minus x squared. When x is 0, we're at 0 times something, so it's 0. And then we go up a ways, but e to the minus x squared weights this thing down, pulls it down to 0 very quickly. Negative exponents tend towards 0 as x gets large. Okay, so we want the area is the integral from 0 to 4 of x e to the negative x squared dx. So we'll let u equal negative x squared, always the entire exponent, then du dx is negative 2x, or du over negative 2 is x dx. And then when we change our limits, when x equals 0, u equals negative 0 squared, x equals 4, u equals negative 16. So this is minus a half times the integral from 0 to negative 16 of e to the u du. Or, changing the minuses and the order of integration, this is a half times the integral from negative 16 to 0 of e to the u du, just absorbing the minus sign by changing the order of integration, or the order of the limits. And this is a half e to the u evaluated between negative 16 and 0. Anything to the 0 is 1, so this is a half minus a half e to the negative 16. Now that's a really tiny number, so this is almost exactly a half. And if you think about it, if you'd integrate this thing and find the area, this gets us to something we'll talk about in a few chapters, all the way out to infinity essentially, you can guess that that would approach the value of a half. And in fact, that is the definition of the improper integral going from 0 out to infinity, as we'll learn later.